So hello dear students, in this video we will be solving one numerical on unit load method, and the concept we have already discussed in our previous videos. So if you have not seen that, please go and check that video, and if you have not subscribed this concrete civil concepts, then please do subscribe, cause lot of many more problems and concepts we'll be discussing in this channel, not only on the civil engineering. Okay, so here we are taking one example or one question from unit load method. So what is this? This is, you have to determine the deflection and rotation at the free end of the cantilever beam. Okay, so if you are given with one cantilever beam with a point load at point C here and one point load at point B here of span L and span L. Okay, and this is your non-prismatic beam, as your moment of inertia for this segment BC is I and for this segment AB is 2I. Okay, so this is 2I and this is I. Okay, and we are having one point load at C and one point load at B. Okay, so we have to find the value of deflection at the C point or at the free end of this cantilever, and the rotation is the same. Okay, so what we need to do, we draw one table. Okay, on this table we are having one description as portion. So portion means we are having two members here. So this is my, if I am considering my origin as C for this segment CB, so this is my CB portion, one portion is CB here and another portion is your BA here. So this is your BA. Okay, this is your BA portion, and the origin, if I am considering my origin for this CB portion is, this is your origin here, this is origin is your C here, and this origin BA is your origin is B here. Okay, if I am considering for this segment BA, the origin is B here, and my limit is, if I am considering my limit by considering my origin as C, so this is my limit is, if I am moving from 0 to my L, so the limit of this segment CB is 0 to L here, and similarly for this segment BA, my limit is 0 to L here, because we have considered our origin as B. Okay, so for this BA segment our limit is 0 to L also. Okay, so this is our limit. Okay, now origin we have completed, portion we have completed, limit we have completed. Now the next is your important is bending moment. Okay, so what is this bending moment? This is the bending moment at any x-axis section at the point where from there deflection is to be required. So we have to find the value of deflection from this C point, and we are considering x-axis section here at a distance of x, and we write the value of bending moment and then write the bending moment value for this CB portion. Similarly, we have to write our bending moment value for this AB segment, and we are taking x-axis section again and write the value of bending moment for this BA portion also. Okay, so how you do this? Now considering your bending moment for CB portion. Okay, so for the CB portion, if I am considering this is my x-axis section here, okay, and at a distance of what, x from this end. So for this CB segment, this is my CB segment, the value of bending moment for this CB segment is, what is this? This is my P value, and this is perpendicular distance is x. So P into x is the bending moment for this segment BC at this section. Okay, so P into x is my bending moment value, and with negative sign because it is in Hawking nature. Okay, so for bending moment x-axis section, the bending moment value for this segment CB is minus P into x. Okay, now we have to consider also our BA segment also. So for the BA segment, if I am considering my section now here, if this is my x-axis section at a distance of x from this B point, okay, because initially we have considered our origin as B for this BA segment. Okay, so now we are considering bending moment section, x-axis section from distance of x from this B point. Okay, so here now we have to write for this x-axis section bending moment value. Okay, now for this section we are having two forces, that is one P force and another P force. Now we have to write for this bending moment for this x-axis section. Now what is this? This P force multiplied by multiplying distances. This is my L value and this is my x value. So P into L plus x is my one force. So this is my P into L plus X is my one force, and another is your P into this is your X distance, perpendicular distance is X. So P into X is your another member forces. Okay, so we have to write here P into X with negative sign as it is in Hawking nature. So minus P into L plus X or minus P into X. So this is the way you write your expression for bending moment. Okay, so M value will be for different segments, that is CV or your BA. Now we have to write your small m1 value and small m2 value. Okay, now for small m1 value will be useful for determining the deflection at this C point. Okay, and your small m2 value will be useful while determining the rotation at this C point. Okay, now for consideration of this m1 value, what we need to do, we just remove these loads. We just remove what? These loads and apply a unit vertical load at the point where the deflection is required. So we are interested in finding out the deflection at the C point. So what we do, we just remove these loads and apply unit vertical load at the C point. Okay, so how? So let me rub it. Okay, this was your question. Now here I remove my external loads and apply unit vertical load at the point where the deflection is required. So this is my C point. Here I required my deflection, so I apply virtual load of 1 kilonewton at the C point, and this is my member here. Okay, now this is my B point, this is my A point here. Okay, now what I do, I write the M1 value, the expression for M1 value for this CV portion and for this BA portion. Okay, so what I need to do, I just take one XX section again here at a distance of what? X from this free end, and write the value of M1 here. So what is the value of M1 here? This is my 1 kilonewton force into perpendicular distance is X. So 1 into X is my bending moment for this XX section. So 1 into X, and it is in Hawking in nature, so it is minus X. So 1 into, so it is 1 into X is minus X. So M1 value for this CV portion is minus X. Okay, now similarly we have to write the M1 value for this BA portion also. So if I am considering here now XX section at a distance of what? X here. Okay, because initially we have considered our B point as origin. So this is our origin here, and now we are considering X distance from this portion, and this is our initially our length is L here. Okay, now write the bending moment value for this portion, BA portion. So 1 into what? Perpendicular distance this time is L plus X. So 1 into L plus X is the perpendicular distance. So 1 into L plus X or X plus L, and with negative sign because it is in Hawking in nature. So this way you write your M1 value expression. Okay, so for the CV portion and for this your BA portion. Okay, now we have to write our bending moment value for this M2 portion or for your rotation part. Okay, so for rotation you need your M2 and you require M2, and we write the value of M2 here and express it for the portion CV and for the portion BA. So what I do, for M1 we apply one vertical load of 1 kilonewton at the point where deflection is required. Now for M2, for rotation, what we do, we apply one concentrated unit moment of 1 kilonewton meter at the point where the deflection is to be required. So I require my deflection at the C point, so I apply 1 kilonewton meter unit moment here, and for that, and we identify and we write the equation for portion CV for bending moment, XX section, and for BA portion. Okay, now what I do, just I rub it here. Now apply here 1 kilonewton meter unit moment here. Okay, for your M2. So now 1 kilonewton unit moment here and apply all the external loads. Okay, so I removed all my P loads. Okay, now for this portion, for this CV portion and for this BA portion, we write the value of bending moment. Okay, so for portion CV, our bending moment value is 1 as we have applied only 1 kilonewton meter, so it is in -1, so it is in anti-clockwise or it is in Hawking nature, so it is -1 for this CB portion, and again the bending moment value is already 1 kilonewton meter, so for this BA portion it is again your 1 kilonewton meter with minus sign. Okay, so this is the way you write the expression for M2 also, by applying your unit concentrated moment at the point where the deflection is to be required. Okay, the important is you have to express the bending moment value with your given loadings, that is your M, and you have to express your M1 value for your deflection, and you have to express your M2 rotation value for your M2. Okay, and we are given with moment of inertia, that is I for this CB portion. This portion we are having moment of inertia value is I, and for this BA portion we are having one moment of inertia value is 2I. Okay, so this is important because when we put in the formula, then it will be helpful and while identifying the I value. Okay, now we have to find our deflection at the free end here. So the formula will be used will be delta is equal to summation of m1 dx upon EI. Okay, now we have already found the value of M bending moment. For this summation means we have to add all the members, like this is my CB members plus BA members. Okay, so I have to write this, I have to apply this formula delta for your summation of integration of what 0 to L for m1 dx upon EI plus 0 to L again m1 dx upon EI. Okay, so for CB plus BA, then this formula will be applicable and the deflection will be required at this C point. Okay, now you see when we apply the values of M or M1, so here this is my delta and we need to find the deflection at the C point. So if this is your delta C here, okay, now it is your, for this is my portion is for BA, so this is for my BA portion here, and this is for my not BA, this is my CB. This is my CB portion here, and this is my BA portion here. Okay, now what is this? Now apply this formula M. What is the M value here? M value is minus P into X. So here minus P into X into M1. M1 value is minus X, so it is minus X here dx upon EA. Okay, plus for this BA portion, for this is BA portion, we apply again the same formula 0 to L. What is this M value for this BA portion is BA portion minus P into L plus X or minus PX. So if I am considering minus A common, so P into L plus X plus PX into M1 value. M1 value for this BA portion is minus X plus L. So it is X plus L here. Okay, now dx upon EI. I value is for this BA portion is 2I. So E into I is 2I. So it is 2EA. Okay, so you have to keep in mind. Now what is this? You just simplify it. Here this is minus minus plus px square. This is x square dx upon EA plus 0 to L. This is my P. If I multiply this x plus L with this with bracket, so this is x plus L whole square plus px x plus L dx upon 2EA here. Now this is what px square dx upon EA plus, if I am considering, if I am taking P upon 2EI as common, P upon 2EI as common, so what is this? And simplify it, x plus A plus B whole square, x square plus L square plus 2xL plus px square here, px square, P already common, so this is your x square plus Lx. Okay, so this is dx. So now we are having 0 to L px square dx upon EI plus 0 to L P upon 2EI. Now we just what? We just multiplying this 2x square. This is your x square plus x square is 2x square, and 2lx plus lx is 3lx plus L square dx. Okay, now just integrate it x square terms. So P upon 2EI, if I am considering whole common, so this is 2 x square integration is x cube by 3. This is 0 to L by putting the value of limit, all the values. Now similarly here, this is my 2x square integration is x cube by 3 plus 3L x square by 2. Here x integration is x square by 2, and this is L square of x. So L square x is 0 to L. By putting the values of upper limit and lower limit, we are getting P upon 2EI 2 into L cube upon 3 plus 2L cube upon 3 here plus 3L x square is L square or L cube upon 2 here plus L square or L cube. Okay. Now after solving by considering LCM, so we are getting delta is equal to what? 23 PL cube upon 12 PL. So this is the way you find your deflection at the free end, and in my next video I will be solving for your rotation for this same question. Okay. So thank you so much.